We're going to be talking about Kneser's theorem in both Lean and Isabelle HOL. Hopefully this is going to be something quite exciting and will allow us to compare the differences between the different formalizations in different systems, really understand what each system has good and perhaps not so good to offer, and what are the workarounds in each that one has to undertake. So just to start off, what is Kneser's theorem? And unfortunately, the connection isn't great, so we might have to wait for the slides to come back at some point. Hopefully they do. Kneser's theorem is a theorem based in additive combinatorics. And additive combinatorics is a part of mathematics that really draws from everything discrete and not even just discrete. So as you can see, it draws from all of these other areas of mathematics and just integrates them into those parts in its proofs and both in the development. It's in general involving questions surrounding the additive structure of sets, and as we'll see in a few slides, Kneser's theorem is exactly about the additive structure of sets. Want to?
Yeah. Okay. So the basic definitions that we care about are of subsets and different sets. So a subset is basically just the set of all additions that you can do between so the subset of A and B is a set of all additions of elements of A with elements of B. And different sets are the same thing with subtraction. The reason we care about this is because these are going to show up as like supports of functions or things like that. So typically, if you care about if you do Fourier, this is how they're going to come up. There's many more reasons to care about them, but this is one of them. And one thing that's going to show up in Kneser specifically is the stabilizer of a set. So here we have a group, usually finite, but actually it can just be anything, abelian group, which acts on the sets of the sets of elements of that group. And this action just like you take each element and you well, if you have a group, an element of the group G, you take each element of your set A and you add G to it, and that gives you a set. And then the stabilizer of that set is going to be the G's for which it doesn't move. So those are like those are very general definitions. And the questions that we can ask is like how big does my set grow when I add it to itself? What kinds of sets do not grow too much when you add them to themselves? Well, a typical example is a subspace or a coset of a subspace. Those don't grow at all. But then you can ask questions of the form, okay, but if I go a bit more, but not too much, am I close to a subspace? Am I like covered by not too many cosets of a subspace? Those are actually pretty deep questions, as we see, much harder than this. And so a prototypical example of that is Cauchy-Davenport. So this is a pretty weirdly named theorem, because as you know, Cauchy was living in the 18th century, like a century before Davenport. And so what happened is that Cauchy came up with a proof that I think he never published. And Davenport arrived much later, and only to notice that he had been spoiled with the result 130 years before. And so the question is, if you have two sets, A and B, go on.
Well, hopefully it comes out.
So you have two sets A and B. You want to, but clearly, assuming they're like finite and non-empty, then the sets of like the sum set of them, A plus B, is going to have at least as many elements as either of them. So you can definitely bound this by the maximum of the size of A and B. And the question is like, can you do more? Because like surely if you have more elements to A, then like A plus B should increase regardless of what the size of B is, unless of course you get to the full. So Cauchy-Davenport tells you that this is actually true in the case of a set of a PZ. And so typical example is like 0, 1 plus 0, 1, 2. So this set has size 2. This set has size 3, and let's say they're all in I don't know. What's your favorite prime number want to be? 7. 7 works fine. Okay. So if I add those two sets, so like this is my A and this is my B, then their sizes they don't quite add up, because you see I don't get it to like 4. This is like 2 and this is 2 elements. This is 3 elements. I don't get 5. Instead I get 4. So this is like 2 plus 3 minus 1 will give me 4. And so like, this is the prototypical example, and Cauchy-Davenport tells you that this is actually true for all sets, regardless of whether there are intervals or whatever. Up to, of course, you can go past the size of your set. And this is a pretty easy result. Like, you know, we did it in a combinatorics last term, and it takes half a lecture, not even, like 10 minutes. And the question now is like, can you generalize it? Because, you know, like Z over PZ is, well, you know, it's a very specific group. So can you abstract the essence of Cauchy-Davenport to more general groups? And that's what Kneser does, if Kneser shows up. Okay, so Kneser is kind of the same statement. It's a lower bound on the size of A plus B. In terms of the sizes of A and B, except that actually you do a bit more. I mean, A plus K, assuming that K is non-empty, is just as big, at least as big as K. So like this is at least better. And B plus K same, except that now you don't have a -1, you have a minus K. So what's this K? Then you have to understand it. It's the stabilizer of A plus B itself. So so it's not as easy as Cauchy-Davenport because now you have a dependence on some group theoretic object. But like, you know, that's still pretty good, right? When you like, just from the fact that this is a subgroup, you can already deduce a lot because assume that your group doesn't have too many subgroups, then K has to be one of these, and so you just run through possibilities, and this is exactly how you can prove Cauchy-Davenport from Kneser. Okay, so wait, okay, so in the case of Z over PZ, K is a subgroup of Z over PZ. There's not that many of them, especially if P is prime. There's two possibilities. Either K is all of it, in which case, well, you know, if you're a set and you're stabilized by all the elements of a group, then actually you're everything, right? Unless you're empty, but we assume that it's not empty. So in that case, A plus B is everything, and fine. That case is a bit trivial. We just ignore it. And if the subgroup is trivial, then actually, can you go back to the previous one? Okay, so now remember that K is the singleton 0. Fine. Okay. A plus singleton 0, that's just A. Fine. B plus singleton 0, that's just B. Fine. And the size of K is 1. Paf, we get exactly Cauchy-Davenport. The Kneser is a far-reaching generalization of Cauchy. So, okay. So now we can start talking about the formal systems. So we use two different formal systems. The first one is Lean, which is, I hope by now, if you've been attending a few lectures of this seminar, you should know, is based on the calculus of inductive constructions, has been developed by Leonardo de Moura since 2013. And by this point, we actually have quite a lot of theorems in it. But the theorems are located in the mathematics library, which is mathlib. And you can see that the proof is exponential-ish. Don't worry too much about the different graphs. The point is like the biggest one. That's what we carry. This is probably not the best picture. Sadly, they removed the old statistics, which are a bit more exponential.
I guess one thing to mention would be that the blue graph is of the Lean 3 mathlib version, and the red graph is of the new Lean 4 mathlib. So the point at which they overlined was exactly the porting effort. Actually, you can see quite a bit of a jump because there was a lot more material going into the Lean 4 library than was supported in the previous.
No, it's not that. It's that they added more line breaks.
Oh, well, as you can see, there was already stuff in the library before that. Yeah. Yeah, so there was a big shift in the systems, but now that the porting is complete, hopefully there won't be a new version of Lean anytime soon. Now talking about Isabelle, the other prover in which we formalized Kneser's theorem, as really introduced by Yaël. It's another modern interactive theorem prover, although this time based in a different setting of simple type theory, which we'll come back to in the not too distant future. Isabelle features very strong automation with the help of Sledgehammer, and it allows the user to also write human readable proofs with the ISAR system. This is something that I think Isabelle has still an advantage over the other sort of modern interactive theorem provers in. Also, many substantial theorems, as compared to mathlib, are formalized in the archive of formal proofs. And here's the growth chart of archive of formal proofs up to 2023. So it's been steadily growing in a sort of perhaps comparative vein to mathlib.
And just remember, strong automation is going to be important for the rest of it.
So we gave a quick note of how the proof of Cauchy-Davenport worked from Kneser. I think we'll not go into the sort of nitty-gritty details of Kneser's theorem in the proof we formalized, but I think a proof sketch is still nevertheless very useful. So here's the quick outline. The quick outline, as you can see, just the statement up top. The first step in which we sort of think about proving this theorem is we want to induct on some sort of quantity based on the finite sets we're extracting from the group. So the proof by Devos, in this case, inducts on the size of A plus B plus A. This is not necessarily the only choice to be made, but it's a very classical one. After the induction step, the first question in which both Devos and a bunch of other authors proving Kneser's theorem in slightly different ways ask is whether the stabilizer of A plus B is trivial. Something that Yaël perhaps sort of remarked in brief is that the stabilizer is a subgroup within the abelian group, and so it automatically will contain at least the identity. So the question is whether this is a trivial group or something, a trivial subgroup or something bigger. And in the case when it is not a trivial subgroup, we open up ourselves to a deduction argument where if we specialize the statement to the quotient group, where we quotient out by the stabilizer, then voila, we have that the sets that we reduce A plus B and A to have smaller cardinalities, and we can use the induction hypothesis. Otherwise, the statement is a bit harder to prove. We need to define some more notions of convergent sets and do some sort of pointwise set manipulations to deduce the claim. We won't go into the details of this because in the different systems they were slightly different, and something Yaël is going to talk about in overall perspective, but they were very much sort of possible to do up to what we know in formalization is sort of these days. So there was a point on why I put this quotient group in red here, and this is going to be the sort of thing I talk about in the next few slides over. The proof by Devos uses the sort of the specialization of the induction hypothesis to a different group than the base group in which the theorem is based in. In different systems, this might or might not be an issue. Essentially, what specializing the induction hypothesis in a different group equates to is being able to quantify over all of your abelian groups a priori when you're doing the induction. Now, quantifying over types is not a trivial thing, as we'll learn. So if you want to quantify over all types in any proof in any type theory, then basically what you need to do is find another type. In this case, let's say beta, where for any abelian group alpha, we can view it as a term of the type beta. Now, whether this is possible or not is a question, and that question is answered in the next slide. So the type theory of Isabelle HOL does not support type universes, which means that not every single type can be also seen as a term of another type. So in this case, we cannot quantify over types. There is no type which, in this case, contains all abelian groups as terms. But there's a workaround. In this case, the quotient group can be re-embedded into the base group G via just taking coset representatives. And once you take coset representatives, then your induction hypothesis can be instantiated now in the base group G with the representation of the group Y an injective homomorphism. It's quite a bit of a workaround in this case. And a similar issue has come up in other formalizations of mathematical material in Isabelle. However, in those cases, the fix, let's say, was slightly different, which we thought was also interesting. And in those cases, it was largely finding that bigger type in which you can re-embed all of your induction steps into, so that you don't need to quantify over, like, let's say, a whole universe of abelian groups. In this case, this wasn't available. However, a nice re-embedding argument was found. And just wanted to show a bit of a snippet of the proof steps that were required to fulfill this re-embedding into the base group. So this was part of a preliminary construction outside the proof. So as we can see, in Isabelle, dash A is just a placeholder for any type. So our function phi is defined to take an element x in a factor group, so a quotient group, and spit out some representative A such that x is equal to the coset given by A of the quotient group. So this again uses choice in this case and leaves the function undefined otherwise. And then we define another group law. So in this case, in our formalization, it was called quotient composition alternative as a placeholder, defined in the usual way, where it just composes the coset representatives. And in the actual proof of Kneser, what we did was we had to reinterpret, and this is something to do with locales that we won't get into this presentation necessarily in. We had to interpret the representative group as an additive abelian group with this new, as you can see, showing up in the same vein, with this new abelian group operation. And this again requires proof. So I've left out the proof here, but it's a trivial one, although something you still have to prove in Isabelle. This allows us to use all of the group theory developed by Jacobson Algebra Library, which we use for our group theory purposes, for the representative group in the re-embedded version, and allows us to finish off the proof in this case. So what's the story in Lean? Part of the reason why the Lean development even came about was to check whether something of a similar nature would arise in Lean. And the interesting way to do this, I found, was not necessarily to immediately think about the theory behind it, but just to try it and then think. So that's why me and Yaël set off to formalize this theorem again in Lean. And thankfully, the induction step sort of only allows you to write a few lines before you really see if you have to sort of think about this re-embedding again, or if quantifying over types is not an issue. So in Lean, the type theory, even though it is dependent types and all of this, really fancy type theory, the thing that really matters in this case, and it's not to do with dependent types, is the fact that it contains omega many universe levels.
Also, Fiero syndrome is the same as inaccessible downloads.
That's true. So what are omega many universe levels? In Lean, they're denoted by type 0, type 1, type 2, and up to any natural number, where each type, alpha in Lean, has a universe level assigned to it. So you can find a natural number such that alpha, it will be a term of type U. So this immediately should ring a bell if you want to think about quantification over types, because every type has a universe level, which means that you can sort of think about it as a term. Should, again, not be an issue when you want to quantify. It also, Lean also implements universe polymorphism, which means that if you say you want to prove your theorem only in type 0, and the proof works for any type n, let's say, then Lean automatically checks it for you and allows you to not have 0, not just have 0 as a fixed variable, but rather leave it as a variable. And whenever the theorem is called, check that all of the assumptions apply and allow you to use the theorem in a polymorphic way. So this is really necessary for the library to use universes, because if you don't have universe polymorphism, what you'll end up doing is proving, n versions of the same theorem, and having to sort of pick and choose between which version you're using for a certain use case. And this is how the proof step of the same sort of part of the proof works in Lean. So again, it's just using induction, and this generalizing step is the step that allows us to push the quantifier out and quantify over all of the Lean groups. So what we're saying is that in Lean, this is not an issue due to the type universes we have. Another thing we wanted to talk about that we found was slightly different between the systems is the way we define stabilizers. This is the first concept to show up apart from some sets and different sets. And interestingly so, we define this very key object in very different ways in Isabelle and Lean. So upstairs, we can see the pen and paper definition, and the Isabelle definition below is very similar, apart from the fact that some set could be substituted for a sum if we wanted to, and we have an intersection with G. To quickly explain this, in Isabelle, in the development we were using of algebra, a group is a set assigned to a given type, which means that in general, if you sum two elements of a type, it might leak over to some element that's not in the group anymore. So in this case, we had to restrict ourselves so that the sum operations are well defined. And then in Lean, the formalization looks slightly different. There's a new object that comes up. This is the not different set. But
actually, this is a bit confusing because we picked a multiplicative version. So maybe I should just notice this. But the correct version of this definition should be like f minus don't fit to sum a to a plus f is equal to s. Maybe I can take over from here actually, because so one big difference between the development of Isabelle, well, not Isabelle itself as a language, but the AFP as a library on top of Isabelle, is that there's no finite sets. There's no type of all finite sets. Instead, you reason about sets which happen to be finite. In mathlib, we made a very different decision from the start, which is we have a type of sets which is called sets. The set alpha is the type of sets of in the type alpha, and thin sets is a type of finite sets. The reason for this is because the original developers wanted to have computational content. This is not such a problem in Kneser because we're not going to like plug in values in Kneser and checking things. But it does make it somewhat nicer for typically for talking about cardinality, etc. Because then you don't have to like prove that the set that you constructed is finite because it's finite by construction. You managed to construct it, so it has to be finite. Okay, fine. But then okay, fine. You have a finite set, and now you want to construct a stabilizer. The stabilizer is naturally a group. It's not naturally a finite set. So can we see why it is finite? Well, actually, it's not always finite, because if I take the stabilizer of the empty set.
Maybe I have to go to the next slide.
Yeah, yeah, you can go to the next slide. The stabilizer of the empty set. What is this? Well, if you add any element to the empty set, you get the empty set. So actually, the stabilizer is everything. That's a bit of a problem. That's not necessarily finite. If we look at, I don't know, if we look at Z and we want to like have a stabilizer of the empty set of integers, then that's everything. That's not finite. Fine. Okay. Let's take that away because Kneser doesn't even talk about empty sets. So what's the next best thing we can do? Well, what's the stabilizer of a non-empty set? Well, if you have some element A in your finite set S, then you know that G plus A has to be in S as well, right? I don't know if you can see. So, okay, if A is an element of S, then you know by the fact that G plus S is equal to S, that G plus A itself has to be in S. Fine, so G plus A has to be in S. That means that G is actually in S minus S, which is the set of A minus B, where A and B are in S. And this is good because this is a finite set. You're just doing operations between finite sets again. So this is what this is doing. So you manage to embed your stabilizer of a non-empty set into a finite set, S minus S, and you just have to filter out the ones for which it actually stabilizes. And the empty set does whatever it does. In that case, we decided to make it go to the empty set.
So as Yaël nicely explained, the reason why we chose a slightly different definition is because we wanted to use the fact that Lean does have a development of finite sets, and we had to make a stabilizer into a finite set. However, the edge case of the empty set had sort of served as a bit of a problem, which meant that we had to have a slight workaround around the definition. So in a way, the definition is a bit unfaithful because we're using knowledge of what where the stabilizer lives before we even define it. And the other thing to mention is the reason why we see multiplicative notation on the Lean side is because Lean allows us to write the same definition both for multiplicative and additive groups and translate it automatically. The notation is usually, and the developments are usually written in multiplicative notation and then translated into additive notation. So in this case, mul would be replaced by add, and the quotient would be replaced, or the division would be replaced by negation automatically, and have sort of a new version of the lemma or definition in the library in an auto-generated way. So I think we've explained the slide together through our.
I didn't explain what filter is, but it just keeps the elements which respect that proposition.
Yeah, it filters out the elements that respect the proposition. Would we have done anything differently? Finishing up on our formalization in Lean, we started sort of to question whether we really need the stabilizer to be a finite set. In some cases, it really was useful, but in some, we found that just having everything live in set might not be an issue, as it really was in Isabelle. Perhaps.
Yeah, because at this point, so I mean, like, you know, we did that like a year and a half ago. This has been a long while, but since then, someone whose initials are like TT is pretty famous. I don't know if you've heard of him. Decided to work on a certain project called PFR, which didn't catch much attention at all. It was like quite tiny. Decided that he needed to do to talk about cardinalities of subgroups for his project. And as it turns out, he made a different design decision to us. I mean, after consulting us and us telling him that, well, yeah, you know, we tried it and it went all right, but it didn't go very well. So he tried, and actually succeeded mostly, given that it made it to a minor pop science journal called Quantum on the 6th of December. If you want to look that up, if you can find it online, I'm sure. And so, yeah, I did, like, you know, I was somewhat involved in that project. So kind of told Mantas, are you sure we did the right thing? And Mantas was like, sorry, I have 3 example sheets next week. That's not at all. So yeah, looking back, I think we might have had better success working with subgroups which were finite, rather than like this weird monster of subgroups which we actually just interpret as finite groups, and because they happen to have nice properties. And or even worse, that's something I had considered at some point, is to have a set which is both equal to a finite set and to a subgroup, and work with that. And like this is probably horrible. We didn't even try.
So part of the reason why we really wanted to go with this definition was the fact that Lean, as we sort of mentioned, develops the theory of finite sets. However, in this case, working with these objects and interpreting stabilizers as subgroups, you really have to talk about its base definition as a subgroup as well. This was not an issue in Isabelle, so it shouldn't be an issue in Lean as well, as Yaël just mentioned. So perhaps we could have gone with a different approach here, and perhaps there shouldn't be a difference in the definitions. However, I think an important thing to note here is that even though definitions were different, the development was largely the same, and the way we proved the theorem was exactly the same. So you can pick your definitions to be different as long as they agree mathematically, and even the formal proofs in at least this circumstance should look the same. I think another notion of the proofs that we won't really look into in detail on the right-hand side of the Kneser's theorem chart, if you remember, where the fact that we used lots of point-wise algebraic manipulations of sets. Just to quickly intersperse to what Yaël is going to talk about in Lean, in Isabelle, we decided not to talk about the handling of algebraic set expressions, partly because it was very easy. And it was very easy for precisely the reason of automation being able to carry all of the work for us. We didn't necessarily need to develop extra lemmas even, because automation was able to handle all of the necessary sort of small steps in handling sets and their cardinalities for us. Whereas on the Lean side, the automation was not so strong, so we really had to think about how to make the formalization less painful. Here, I'll take.
Okay. So yeah, let's talk about. Let's say I want to talk about two sets. So these two ways I could do this. The first way is where I just calculate every subtraction one by one. Okay. 0 minus 1, path, 0 minus 2, path, 3 minus 1, 3 minus 2, 4 minus 1, 4 minus 2. Good. Okay, that gives me some set I can figure out. What I mostly care about is that this is the same as it's the same as adding the negation of the set on the right. But those are fundamentally different operations. I mean, if you go through the calculation, instead of subtracting the things one by one, you first start negating the ones in the right set, and then you do 0 plus minus 1, 0 plus minus 2, 3 plus minus 1, 3 plus minus 2, 4 plus minus 1, 4 plus minus 2, and you get the same result, of course. And this looks a bit trivial when you look at a concrete example, but when you manipulate the expression within the form of theorem, those have very different expressions in terms of logic symbols. One of them is two existential quantifiers with an equality inside. And the other one has two existential quantifiers, plus one more, which is the membership of the negation. And so this starts getting a bit complicated, because now if you want to simplify that, you have to swap this negation around, simplify the basis to actually B is just equal to minus something, and then equally to B minus something, and then do A plus minus something is A minus something. And then you get back. Great. Okay, that's fine. So I'm happy to do that once. This is fine. But I don't want to do it at every line of code, because if you take the usual proof in Isabelle, it looks like this. This is equal to that. I don't remember the syntax, but basically by
By.
And then something else. I don't know. You have so many violent names of tactics. This is exactly how I feel when I read Isabelle scripts. And so like, this is some set expression, and then you rearrange it around, and you get a different set expression, and then you like do functionality, you move stuff around. Like you do this, right? You exactly like go from one to the other, but like this is a violent operation. And I'm peaceful at heart, so so this was not really a solution to me. I mean, mostly Lean is lacking the automation. Nowadays we do have a better option, which is called the ISO. But this was not there when we started the project. And this was not there, and mostly this still forces us to like state every equality that we use. And I wanted to recover this rewriting feeling of just I take an expression, then I modify a sub-expression without even telling Lean what sub-expression is going to rewrite, because it can figure it out. And just like doing this chain of rewrites and working as you would work on paper without having to state everything in the middle. And so like the typical equalities that I need for this like rewriting reasoning to work out are like discount. So of course you can swap two sets, assuming you're for the billion, fine. Negation is involutive. Negation of sets, not negation of elements, because negation of elements is of possibility. And then if you like path, whatever, a bit more. But like you see, it can get quite complicated. Like this is well, okay, this didn't show up, but things of this complexity do show up in the calculations. So maybe not Kneser specifically, but I worked on like the Prunecker triangle inequality, and this shows up. So the Prunecker triangle inequality is about sets of the form like LA minus MA. And so then you do induction on L and M. So like there's more A's that appear on one side, more A's that appear on the other side. You want to like, well, you can cancel them out. That's not allowed. But you can like reassociate things to really qualities, whatever. It's a bit of a pain if you have to do it by hand. So the problem at heart, which is like why this is not easy, is because all the theorems all like the inequalities that I just stated are true in any group, except that finite sets do not form a group. That's a bit of a problem. Why is that? Well, because of our non-friend, our enemy, the empty set. Because if you like the empty set added to anything, is the empty set, and so certainly that's not like a group doesn't act like this. This is not a group like a thing that's happening. So fine, you can't have it all. And maybe another thing which is going to think about is that if you do A minus A, this is definitely not like zero, whatever zero is supposed to be. Like this is very big. Like when you take A bigger, this is going to like grow and grow and grow. So this is definitely not a group. This is just not a group.
In fact, Kneser gives you a bound on the. Yeah,
Kneser gives you a bound on this. It's quite fun. Okay, so fine. What do we do? Yeah, so I already explained the Isabelle solution. The Isabelle solution is everywhere.
And it works very well.
Fine. The solution that I took in Lean was to find something weaker than a group where all of the inequalities that I stated are still true. So now the question is, what kind of inequalities are actually true for finite sets? So next one. So this is where we notice things. If you look up 2 slides ago, which we can do in like a second, but just bear with my no, just wait. So okay, fine. If you look at all of them, then you see that the number of summands in each for each set, well, each set appears the same number of times on the left and on the right. So and importantly, it appears with also the same sign. So typically, this minus b here cannot become a plus b there. Well, unless you're a characteristic too, of course. But okay, go back. Plop. And also, you're not allowed to like you don't have distributivity. If you look at this thing, typically there's one A there, and then there's like 2 A's here. So if you look at the quantifiers, the left-hand side is going to be a big existential in terms of like elements of one element of A, one element of B, one element of C. And you would like this to be the same as an existential, which is term of one element of A, one element of B, one more element of A, one element of C. This just doesn't work. There is an inclusion one way, but it doesn't work the other way around. So okay, so these are not allowed. You can also cancel, fine. You cannot change the sign, fine. Okay, so what do we do? What do we do? We go to the next slide. and we find the quintessential identities from which everything else follows. Well, almost everything else follows. And so the ones that I took, there's actually quite a few more that you could have picked. So this is not like the ultimate list. It's just one which is pretty practical for many cases. Is that subtracting is the same as adding the negation? Fine. Negation is involutive? Fine. And that negation is distributive, well, actually anti-distributive to care for the non-evident case over addition. And this is where the insight comes in. This is enough. We don't need anything more for most applications. So this is the definition in it. Pretty simple and pretty nice. And now remember this non-implication between A group G and A group field set G. Well, this time this is true. If you have what I call a subtraction monoid, I hope you like it. I'm sure it already exists somewhere in the literature. Well, not the name. The name exists, but probably not the algebraic object. If you find a better contender for the name, please yyd23@cambridge.ac.uk. I would be very happy to hear the suggestion. So if you have a subtraction monoid and you look at finite sets of that subtraction monoid, those also form subtraction monoid. So you've won, because now you can generalize all the lemmas that were about groups to that subtraction whatever thing, and now they all apply to finite sets. So you've won. But actually, you've won even more if you go to the next slide.
Just before I do, I just wanted to refer back to the type universe as part of the presentation, and as you can see here, G is allowed to range over any type universe where U is a variable.
You get even more because, like as Mantas explained a few slides ago, we do everything twice in mathlib, which is probably not very convenient for some reasons. But we do everything twice. We do everything in the additive world and we do everything in the multiplicative world. So subtraction monoids also have a multiplicative analog, I guess, well, equivalent, which I call the right-free division monoid. And division monoids, well, they are like they can prove identities of this form. So this is basically the same as before, right? This is like if you like additivize everything, if you replace the inverse by a minus and you replace the division by an egg, then you get something which you can get from subtraction monoids. And importantly, those equations hold in mathlib in both groups and groups with zero. So what's a group with zero? Yeah, you ask. Well, a group with zero is a group, except that it has a zero. So it's not quite a group. It's almost a group. And so what's a typical example? Well, let's say you take the real numbers. The real numbers, if you remove zero, this is a group. Fine. But if you add zero, right, this is almost a group, right? You have A, and you have A times zero, which is equal to zero. And you have 0 times A, which is equal to 0, whatever, and everything is respected. And the one thing is you cannot divide by 0. This is what a group with 0 is. If 0 is absorbent, without 0 it's a group, and with 0 it's almost a group. And so if you look at A divided by B, so let's say I do A divided by 0, because this is supposed to make sense. All the operations are total. A divided by 0, what is it in mean? We decide that dividing by 0 gives you 0. This is a pretty useful choice, as it turns out, because A divided by 0 is going to be 0. So that's A divided by 0 inverse is 0 inverse. And now you are dividing by 0 again, so this is 0. And this is equal to 0 divided by A. Because 0 is absorbent, you get to propagate the junk value of the division by 0 everywhere. And this works out for most cases. And also, typical example is like if you do A over 0 plus B over 0 is equal to A plus B over 0. Because both sides are 0. This is stupid, but this is actually very useful because it gets rid of many side conditions. So A over C plus B over C is unconditionally true in the real numbers in mathlib. But now that the proof was not the same as in the case of groups because you had to do a case analysis on whether your denominator was 0 or not. So they like those lemmas that prove that A over C plus B over C in the case of, well, okay, that's not an example, but like A over B, the inverse equal to B over A, they have to be separate lemmas for groups with 0 and groups. Or can they? Maybe we can actually do everything with one thing. And maybe this is what division monoid does exactly. So division monoid, well, I didn't check the latest number, but when I introduced division monoid in mathlib, it got rid of approximately 500 lemmas that were proved separately for group and group with 0 and made them all into one. So like divided the number by half so that we went from 1,000 lemmas to 500. And that's one of the single most unifying changes to mathlib.
Is there a tool that checks
For the checks for 0?
that checks for the subsumption of a result by another result?
Yes, there is, although I'm not. It existed in Lean 3. I'm not sure whether people have more to have more on it in Lean 4.
How did you discover there were 500?
So how did they discover they were 500? Because I did them by hand. But the better answer is that Alex Best has worked on a tool which automatically checks whether you can weaken time class assumptions. So typically replace groups by monos like division monoid. In that case, I know it's 500 because now, or at least at the time, last time I checked, there were 500 lemmas which were about division monoid. And I made sure that those lemmas did not duplicate anything anymore. So that means that they replaced group and group with 0 lemmas that were previously duplicated. And last thing, I told you that I could get almost everything with those axioms over finite sets. There's one thing which I cannot do, namely I cannot state that the inverse of something is equal to something. I just cannot get that out from my other equations. This never shows up, and this never happens for finite sets. Like like the inverse of a set is I can never get the fact that two sets are multiple of 1. I will multiply to 1 because 1 is like singleton 1. So like multiplying things to a singleton, this never happens. So I didn't need that for finite sets. But in the case of division monoids, so like groups and group with 0, this showed up much more. So I added it as an extra axiom, and it makes things.
So just before we conclude, I think in the interest of not making like sweeping generalizations, just to go back on the handling of algebraic expressions, on the Isabelle side, even though we used the formalization a fair bit, we still relied on previous developments. And those previous developments were developed in particular in the Plunike-Ruza development, which is in the AFP, developed by the Alexandria group, whose past collaborators and members are sitting in the second row here. So we really relied on those developments and we reused them. But I think what we wanted to say was that the level of API we had to develop in Lean and Isabelle were basically close to an order of magnitude different, simply because of the automation available in Isabelle, which is not available in Lean. So in the case of Isabelle, we didn't have to think about it that much. In the case of Lean, we really had to think about it. And now to conclude, we also computed the Born factors. Not to say that these are of any particular great sort of scientific value, but comparing the compressed sizes of the proof of Kneser's theorem in Lean and Isabelle, they're quite low, which is quite surprising. The man hours spent formalizing the proofs and perhaps making that DevOps spent making the proof work probably are still a bit different.
I think it's actually inversely proportional to the Born factor.
Exactly. The reason why the Lean the Born factor might be lower could be due to the fact that, as we said, we develop more API specific to the proof in Lean, and also because of the sort of different community guidelines surrounding what a proof acceptable for a library looks like. However, both are still very low factors, so we should be happy with both.
I mean, maybe caricature, like when you want to get something into the AFP, you bring a message to Larry and he says, yeah, sure, and then it gets in, or like mostly. When you want to get something in mathlib, well, you send one for request, which contains like maybe 1% of your total thing, and then it sits there for like months. And at some point, you ring up Johan Comlin and you're like, okay, but like, come on, Johan, it's been a while. And then he says, oh yeah, sure, and he's merged. And then you could do the second percent, and that takes another one. So right now, the proof of Kneser is in the AFP, but it's not in mathlib. Because of this thing about stabilizers not possibly being the right thing defined as finite sets, etc. And so even though we probably spend more time on the Lean formulation than the Isabelle one, because what usually happens when you in Isabelle you just wait for the proof with your blast thing, whatever. In Lean, like when one lemma reaches 10 lines long, you're like, oh my god, this is way too slow, and so you split it in half. And when you split it in half, usually what happens is that it's not really a lemma about your proof anymore. It's a lemma about the more general thing. So the lemma about the more general thing ends up in mathlib pretty good, but the other half is still there. And so you get rid of a lot of code like that, because you get more preliminaries out of your big juicy theorem, and like you squeeze it hard, and you get like, well, you get the juice comes out and drops into mathlib, but then the bulk itself stays in your repository forever. Nobody wants to drink it, right? So that's why Lean is smaller than Isabelle. And maybe I should also mention why do we zip them? Because it gets rid of things like blank lines or comments or like repetitive things. So it's a more accurate representation than just, oh yeah, my PDF was 1 megabyte and my Lean formalization was 10 kilobytes. So my different factor is 1/1000. Like it's not really common.
And to finally conclude, I think we should say that additive combinatorics is verified by both the Lean formalization and Isabelle formalization, an area suitable for many and probably any modern proof assistance to formalize. So hopefully we can have even more contributions coming in the not too distant future. And also to say that even though there are very tangible differences between the systems, formalizing is still largely very much possible and attractive as a way to both learn about the proof assistant, learn the mathematics, and sort of gain a better understanding of the areas involved. I think it probably is a good time to ask for any questions, given that we have a few minutes left. Yep.
I actually have two questions. So the first one's a simple question. When you mentioned the number of lines in mathlib and AFP respectively, they look like they're about the same, about 150,000, unless I misread.
I think that everyone has much more.
I think so.
Yeah, that's what I thought.
So
yeah, I just misread that.
Yeah.
So about 150,000, you know, right? That's mathlib 4.
No, 1 million for 1.4 million.
Oh, that's like that's what I missed.
This is
The AFP is not all mathematics, however.
yes.
Yeah.
And also there is another part of the Isabelle libraries which are not in the AFP, which are the standard libraries.
I see. Okay, yes.
Well, I mean, the standard library is not that big.
It's not that big.
It's not. I think the real difference is that all the juice gets squeezed before you get to mathlib, and the AFP is a bit more liberal about inclusion, so you get.
Yeah. Okay. Yeah. So I mean, I'd originally thought that Isabelle had way more theorems proved, but I guess that's still possible.
I think it has more theorems proved
Yeah.
because it's been around for longer.
Yeah.
And then the AFP contains more things because of the community difference that you get inclusion more easily than in mathlib.
Yeah.
So in mathlib, there's a bunch of projects hanging around that everybody knows about, but it's not in mathlib because people haven't worked hard enough to make that happen.
Right. And my second question had to do with this type universes. Question of the type theorists in the room, of which I assume there are many. Is it possible to have something like simple type theory, so not necessarily simple type theory, that has type universes?
Yes, perhaps I should have mentioned this already. The answer is yes. And there's been developments on top of, in particular, the HOL system, In fact, at least in that architecture, to extend it to have type universes, both to have at least 2 type universes, which in most applications turns out to be enough, but also to have omega many type universes.
So is this a fundamental thing though, at the level of type theory, or is there some kind of hack to build it onto simple type theory?
I don't think it's a hack. It's,
Yeah, so it's formally
Yes.
possible to do.
well, you still need to prove semantics and sort of related things, but
Yeah, of course.
yeah, it's been done and it's possible. Talking to Larry before in an email exchange, I think I don't want to misquote you, but I think you said that it's like the development of type universes for Isabelle would be tangential to the needs of computational logic.
Well, some people had done some experiments, but they were not, I think, regarded as worth it enough to really continue it. Because in simple type theory, you're using types in a completely different way, and so the need doesn't arise.
Yeah. Yep.
Yeah, you were talking about the community differences. Do you think the mathlib is so stringent about who gets in because the automation's poorer, so you need more sort of like
There's definitely like more of a burden because I mean, Larry, you probably know about this more than I do, but like how is the AFP maintained? Because you do like a monthly release or something like this?
Anytime anyone changes anything, if it breaks something in the AFP, they have to fix it, but it's usually not difficult. It helps having structured proofs, and automation means if something breaks, usually you can figure out and you could just fix it.
Like, yeah, how many breaking changes do you get?
I don't know. I mean, it's okay. If it's a big change, you might get 20 things, and it's a bit tedious too. But usually each one is not too much work.
In mathlib, we have about 20 breaking changes a day. So
I think part of the reason why we get breaking changes is because we can't develop alternative definitions of the same thing. So this is the mono library approach where there's only one and only one definition of the same mathematical object. Whereas in the AFP, some of these entries have developed graph theory in multiple different ways. So you're much more incentivized not to make breaking changes when you are allowed to make different definitions. And then sometimes if you have to make breaking changes, maybe there's a workaround where you don't.
yeah, I think Isabelle is mostly like one of libraries that people people rework them after the fact, but not that much. Like in Lean, there's no file that has survived more than 2 months without a change. Everything gets just trampled all over again all the time. So I mean, personally, I'm keeping up several projects. So PFR including, but also my Fourier analysis library. I keep them afloat, but it's like a constant maintenance need. People are working on that. There's so Mario Canero specifically has some ideas about how we could do automatic migration of Lean projects that depend on mathlib. This is not a trivial task because you have to take care of the syntax, of the theorems. Like it very often happens that you're running a theorem to something slightly different because it was slightly wrong or whatever. And then sometimes you move files, and then there's many different things that can happen. And you would like to do most of them automatically, and but this is not there. This is not there yet. So I have to everything breaks in my library every week.
So the feeling is that Isabelle formalization was not very useful to do the Lean formalization, aside from the fact that Mantas already knew the proof because we did it first in Isabelle and then in Lean.
I think that was a big part of it.
Yeah, so you knew the proof because we finished it first in Isabelle around the summer of the 20.
I think the domain.
And then we did it over Christmas. But I mean, other than that, there is no way that the code is really directly helpful.
No, it's the Mantas.
Yeah, it didn't really help to directly.
No, yeah, Mantas learned a lot about type universes and how to run the induction argument, but it was completely useless to me because it just worked.
Yeah.
Sorry.
Yeah.
But I think still, I think the general notions of the API needed to develop, sort of the stub of what I developed in what we developed rather in Isabelle, sort of had to be translated into Lean and then upgraded, because, you know, in Lean, as we said, handling expressions is a lot harder. So I think it was a sort of very important first step, definitely. Probably the other way around would have been a lot easier as well, I think. Well, given that, you know,
Yeah.
we knew the workaround, if we had developed the Lean project first, then Isabelle formalization follows like even more easily, I think.
I think is that we actually should go back to the slide with the blueprint and explain one more thing.
Sure. I don't know, we're sort of running past the time, but
So now, since it's already 5 past, we can maybe applaud and thank our speakers.
Okay.
And anyone who wants to stay for further question is welcome to post them as long as you want to answer. But if someone needs to leave, that's not an issue.
You have one more before I go back to the slide through.
I mean, I was wondering if you then eventually develop something like Ring to decide these kinds of inequalities that show up in subtraction models.
Like Ring, the existing tactic, you mean?
Yeah, like I mean, like do you feel that having a decision procedure for subtractive for the theory of subtractive model could have helped?
I think it's hard, specifically because all the existing procedures that are in the literature, like automatic normalized, like form or normal form, something normal form, and you don't have a really normal form because you can cancel things out. And
Okay.
you have to, well, okay, you can throw away the order of terms, but that's mostly it. You can you have to like it's not. There could be a decision procedure for that, for division mono specifically.
Yeah.
But I'm not sure there would be a great field because like most division monoids are actually groups. Like things that are kind of the exception.
Mm-hmm.
And the status in Lean of decision procedures is that every time you have a new, when you care about a new algebraic object, you kind of write its own decision procedure, which uses its own heuristics. So you know you have ring, you have able,
Yeah.
you have a group, you have a non-com ring. Why is non-com ring thing? Could it just not the same thing as ring? Like then you have field sim, which you are supposed to use on top of ring. I wish like things were more unified. If things were more unified, maybe we could just like plug it in on the existing one. But if it involves like creating a new one and having people remember it, I think it's not worth it.
Okay.
I think it's not worth it. So maybe slide 3 just for the enjoyment of people. Yeah. At this point, this is actually kind of a weird induction, if you think about it. Because what's happening really when you do the induction is that you notice that so K's are stabilized. K is like so when you see that the stabilizer is not trivial, what does it really mean? It means that like you have your set A, and you have your set B, and then you have a well, I think that's one thing about the guess you also have A plus B, which if you look like this. So this is A plus B, this is A, and this is B. And claiming that K is non-trivial is the same thing as saying, well, actually, I can do just like I can cut A into similar bits, which are all like cosets of K. And I can also cut B with those same bits. And if I can cut A and B with those bits, then that means that A plus B also can be cut in those ways. So what's really happening is that you're saying, well, okay, if I just contract the case, I get the same picture with less things on, with less elements. So in particular, you never do this induction hypothesis twice. Like it's barely an induction. Like, you know, you go there, bam, bam, bam. Is a K trivial? No. Okay, apply induction. Bam, bam, bam. Is K trivial? Yes. Okay, go on with the proof. So it's sometimes very wasteful to make it an induction hypothesis. This is really a simplifying assumption on paper. And in retrospect, we should not have done this. We should have just have gone with like a special casing, or maybe even just keeping the concepts around and keeping like extra terms everywhere. It would have been so much easier than trying to find simple type theory. But we didn't know it was going to be that hard.
Was it really difficult to make this, thing? with
Once you have the
subsets?
idea, no.
No, I would have thought it was really
No.
straightforward.
I think the point we're trying to make is that we wanted the formalization to sort of reflect the latex document essentially that we were sort of using for our formalization. And then in this case, it actually differs. You actually have to do something non-trivial that's slightly different. I mean, once you know what to do, it's then.
Is there, can you think of any like theorems where this actually becomes a bigger pain, where you're like having to do this induction on types?
So I think talking to Larry and a bunch of other people in the Isabelle community, similar issues have been sort of seen in the case of developing algebraic closures. When you're thinking about embedding into polynomial, sort of into what's the?
Well, you do directly construction.
Yes, but in that case, you can develop this other type in which all of your newly constructed extensions embed into, and then you can sort of project that.
Enumerate the algebraic.
Exactly.
Yeah.
But in this case, that's not a way to go through. So I think, yeah, that's another thing that I found interesting.
Yeah, finite group theory, you can have finite sets. Yeah, it feels like any particular theorem you have, there's some trick you can use to avoid them.
For actual mathematics, well, actual, I'm using.
Yeah, for like
Perhaps
human math.
Yes.
Yeah.
I think the problem here comes up with sort of statements of the form where you want to prove universal properties about some object. Then it's difficult, or rather about some definition. So
Usually in category theory.
yeah, something
when you
universal properties in category theory sound like something that is unlikely to happen. But yeah, for regular mathematics.
The formalization builds on Angeliki Koutsoukou-Argyraki, which builds on an alternative. So we didn't use the standard Isabelle library. We used an alternative algebra library, which is on the AFB.
Check it out. Yeah.
So.
Yeah. I've seen it. Yeah. That one's the like purely locale based one, right?
Yep.
No
record.
What they call records. Yeah.
Yeah, the old algebra library, I mean, it's from like 1999, and it really needs to be completely redone.
That one's whole algebra, right?
Yeah.
And then there's the even older one, which is type classes.
Well, no, that was never about algebra.
Oh, okay. So
I wanted to comment, the two Isabelle definitions that you showed, they both looked like they were written in a defensive way, like you're trying to deal with the possibility that it's applied to something outside its expected domain and then fix it. Now, without actually doing your proofs, I can't be sure, but I think both there and with the previous one, you could simply assume that you're going to apply it within the expected domain, and probably everything would be fine. And if it wasn't fine, of course, all that would be reflected in is that your proofs would be a bit more cumbersome than you wanted. But there, I would get rid of the intersection with G, and the previous one, you had an if then else undefined. Which I think you could get rid of that completely and just have the breaker. So, unless you discover that it was causing you problems, of course.
So
for the purpose of maybe using them different developments, maybe let's say it's better to use.
Well, it's better to have the simplest possible definitions. And this also applies to Lean, I'm sure.
Well, didn't you make
so, but in the problem here is that any element of the stabilizer, then you wouldn't know is in your base group.
So if S is a subset of G, if S is a subset of G to begin with, is it still possible the sum set could go outside? You know,
yes,
it isn't.
yes, because the sum operation is defined on the type and not the set itself.
You know, because the sum set, doesn't that take the group addition operator?
Yeah.
And the group is closed under that, and X belongs to the group presumably. S is a subset of the group, and therefore the subset.
Okay, yeah. So this one isn't necessary. I agree, but this one then is.
No, and then
because S itself.
Well, and if in your hypotheses you have S a subset G somewhere.
Yeah, but in this, yes, I agree. You would have to then instantiate that hypothesis. So basically, I think what we're sort of perhaps slightly disagreeing about is that in one case, we have to instantiate the hypothesis that S is a subset of G, and in the other case, we say S intersection G is S. It's just a bit of, but perhaps for the definition, it would have been nicer to write it with just with that.
Yeah.
It wouldn't cause any strain on the automation, right? If you just, like, it'll always get found and you could even put it in the center.
Well, if there's no any questions, I think we could time to conclude.